All right, in this video, we're going to look at calculating volumes, our first video in a quick series here of calculating volumes. So if we imagine a three-dimensional shape, how do we find out how much volume it has? And this is going to depend a bit on the exact nature and kind of type of shape that we're talking about. So first, we're going to look at geometric cross sections, as you saw kind of previously. And here's the main principle. We're going to slice the volume into uniform geometric sheets and then integrate to combine. It might be better to actually say similar here. By uniform, I mean the same kind of shape, but similar is probably a better word here. So for example, if you had a square-based pyramid like this, and you imagine slicing it kind of horizontally like this. This is your slice, so it goes back across like that. You can imagine that each of those sheets is a square, a poorly drawn square, but at the bottom you have a big square, and at the top you have tiny, tiny squares. That's the idea here. Or if you had something that was, let me see if I can sketch this well. So imagine kind of a half of a cone sort of shape, where each of these vertical cross sections are semicircles. So you can kind of imagine that would look something like this. And so each of those slices is semicircles. So always thinking about slicing it like a loaf of bread, and what do those bread slices look like? So let's look at it with the geometric cross sections here. So the base of a solid S is the region bounded by the parabola x squared equals 8y and the line y equals 4. Cross sections are perpendicular to the y-axis are equilateral triangles. So we have cross sections are perpendicular to the y-axis. That means we imagine something like this, and it's going to come kind of out of the screen here as an equilateral triangle. So if I draw this kind of on its side, or from a different perspective, you can imagine it's something like this. And then at the end, we've got a triangle. And then in the middle, we've got, a triangle. And as we go along, it should be something like that at the top. So it's very similar to what I had before, but it's got a nice sharp peak. So it's kind of like a tent, if you want to think about it that way. You can kind of imagine all these triangular slices. And the width of those triangular slices you see is this width right here. So what we want to do is integrate, and we're always going to multiply area times thickness. So the thickness of these slices is dy, because it's a delta y, a tiny, tiny change in y. So I know that I'm going to be integrating with respect to y, and the thickness, or the area, is going to be 2 times x, because that's the length here, right? This is x and this is x, each of those. 2 times x times the height, which we'll need to sketch that out to figure out the height, divided by 2. Or in other words, it'll be x times h. Now what's h for an equilateral triangle? Well, we know that this is 60, this is x, so the height is going to, and this is 2x, the height is going to be 2x sine of 60. or if you prefer, h is equal to x tangent of 60. But that's our height, and that's just from the geometry of the trigonometry of this triangle. So coming over here, we're going to have x times 2x sine 60. And we're going to integrate from 0 all the way up to whatever y equals 4. But we run into a problem here because this is an x and this is a dy. So we need to change these x's to y's. And again, just remember that this was just the area, 2xh divided by 2, and then which is xh. H from the trigonometry is 2x sine 60, and so this right here is just area, and then thickness. So let's clean this up a little bit, and I'm going to erase that. So at this point, we've set up our integral. Now we're just trying to figure out how we're going to actually integrate. So I'm going to start by pulling out all of my constants. And we'll deal with those, at the end. Integrate from 0 to 4 of x squared dy. So now the question is, how big is x? Well, we know that x squared is equal to 8y is going to be our curve. So each of these slices, depending on where I am with the y value, I'll get, a given x value. So the nice thing is it's already written in terms of x squared. So 2 sine of 60 integral from 0 to 4 is 8y dy. And then if you integrate that, you're going to get 2 sine 60 integral from 0 to 4 of 8y, so that'll be 4y squared from 0 to 4. And you can go through and do the rest of the math to get the number for that. But that's the idea here, is slice it, find the area of each slice, and don't worry about what variables it's in terms of, just label the easiest ones to do. Then write your thickness, write your area expression, and then at that point, if you need to start swapping in new variables, you can do that. So that's the idea behind geometric cross sections. We'll look at rotations and kind of more complex things in the next couple of videos.